This is 2013 question 6 from a pre-paper. Now, I'm not going to do the first two parts because you should be able to define those. I'm going to start with that. So derive a formula T is equal to 2 pi root m over k. And then we have a question on tidal movements. So a tidal movement results in the change of depth of water in a harbour during the day. This depth changes as time goes by and can be described with simple harmonic motion. The depth of the water is 25 meters above the ground level underneath the sea at high tide, and it's only 12 meters at low tide. A boat is going up and down executing simple harmonic motion, and we're looking for the period, the amplitude. When will the boat next be at next after low tide will it be moving at its fastest? Calculate the force at high tide and find the two depths when the force is 1 by 10 to the minus 3 newtons. I'm not going to do the last part. So, the derivation, first of all. Any system that can obey Hooke's law can execute simple harmonic motion. It's a mandatory derivation. And I start with this. F is equal to ma. We sub that into the Hooke's law equation, divide under by the m. And that tells me then that a is proportional to minus x, so it shows that it executes simple harmonic motion. The formula for simple harmonic motion in the log tables is the top one. That's what we have. So when you compare the two, you see that omega squared is root k over m. Now, if t is equal to 2 pi over omega, then you can sub that thing in there in the square root into that, and you get 2 pi root m over k. And that's the proof or the derivation of that. Okay, onto the tidal movement thing. So what happens is it's at high tide at 10:20. We're told to execute simple harmonic motion. So we've got a kind of wave thing going on there, a simple harmonic motion wave. And it gets to low tide at 4:40 p.m. and it's a height of 12 above the ground underneath the sea. So the tide goes like that to that, up and down, but there's always water there, so the ground is underneath. Okay, let's start with the amplitude. So the amplitude is the distance from there to the middle point, the equilibrium position, or from there to the equilibrium position. So if I subtract those two heights, that's twice the amplitude. So the amplitude is half of the difference between the two, which is 6.5. The periodic time is the time taken to repeat itself, the time taken to go from there to there. So time taken to go from there to there is half a period. So if I subtract those times, I get 6 hours and 20 minutes and then double it for the period. So that's it. T is the time for one full oscillation. The time between high and low tides is only half an oscillation, so double it and you get 12 hours, 40 minutes. Okay, the next thing is, when is the next time after low tide the boat will be moving its fastest? So, I don't know if you can read it there. The boat moves fastest as it travels through the center of oscillation. That's always the same for simple harmonic motion. So that's when it's traveling along the horizontal line of the graph. So it's a quarter of a wavelength distance from there to there, or what I should have said, it's a quarter of the period from there to there. So we know a quarter of the period is that time there. Look, it's a quarter of that value, 3 minutes or 3 hours and 10 minutes. And it's how long after low tide. So it's 3 or 10 minutes after that time, which I've converted to a 24-hour clock. Gives me 19 hours and 50 minutes or 7:50 p.m. Okay, we're almost there. The next one is calculate the force at high tide. So let me just get organized. Okay, what we have is the height varies. It goes from a maximum to a minimum. And remember that the acceleration is proportional to F. So F is equal to ma. So when the force is a maximum, the acceleration will be a maximum. And according to simple harmonic motion, which is a is proportional to minus x, the maximum acceleration is when the x value is maximum as well. So it's at the extreme. So maximum acceleration and force there and there and there and there at high and low tides. And just for completion, there's zero acceleration or force at the horizontal position or at the equilibrium position. So what are we looking for? Calculate the force experienced at high tide. You would just use F is equal to ma. The acceleration is omega squared x. The x value is the height above the equilibrium position. So you should be able to work that out. So you'd have F is equal to ma. So F is equal to m omega squared s, where s is the amplitude of the motion. You should be able to do that. The next one, find the two depths of the water where the force on the boat is 1 by 10 to the minus 3 newtons. So keep an eye here, look, maximum at the extreme, and it's also 0, that should be 0 at the center of oscillation. So that means that that force is somewhere near the center of oscillation. And we'll do the same thing as we did, or I suggested in the previous question. You've got your force is ma, the acceleration is equal to that. Now we're looking for the displacement with that acceleration. So a is equal to minus omega squared s. You can always use that for simple harmonic motion. S then is a over omega squared. You have the a value, you need the omega squared value. You don't have that, but you do have the periodic time. So if you use t as 2 pi over omega, omega is 2 pi over t, you should be able to get the omega value to sub in there, which is what I've done. And you just need to convert that to seconds if you go about it the long way. Now, that question won't be finished if you get the answer there, because the value for s that you get is the displacement from the equilibrium position. So if you got 1 meter, what that would mean is it's 1 meter above or it's 1 meter below. So you'd have to get the height above the line there with which it's above the ground. And when it's below the horizontal line there, you'd have to get the height above the ground as well. And I leave you get that yourselves.